So, so far we established that the dynamics of space-time can produce particles. And that happens when the mode oscillators have some non-adiabatically fast evolution. Which meant that, for example, if omega prime divided by omega squared is larger than 1, that's when it happens. That's when the change in the frequency of a harmonic oscillator is fast compared to the natural frequency of the harmonic oscillator. There's got to be a square here just to make the units come out right, so that the whole expression is unitless. So then, is that important in cosmology, however? Well, it's been proposed that our universe may be static, and it may be expanding forever, and it may be not diluting, or it may be diluting, but still keep a constant matter density because matter is being created through the expansion. That was a viable theory until about 20 years ago or so. But now we know, of course, that there is a definite evolution in galaxies and stars, and we know that far away and therefore early galaxies just are different from the ones that we see now. For example, less metallicity, there's less debris of supernovae explosions, and so on. So it seems that this effect, while important in principle, isn't really important for cosmology. Black holes is a different story. There it's really about particle creation. But for cosmology, there is some other weird phenomenon that dominates the scene. And that is the phenomenon that we are going to cover now. Namely, the phenomenon that space-time dynamics can not only produce particles, it can also enhance quantum field fluctuations. Ultimately, we want to describe the cosmic microwave background as having originated in quantum fluctuations. And this is not about particle production. This is about field fluctuations. And when does that happen? Well, that happens when something even more dramatic happens to the harmonic oscillator's frequencies. Instead of the case where the frequency changes quickly as compared to the frequency, no, that is the case where the frequency goes imaginary, where the frequency squared becomes negative. If you remember, the harmonic oscillators for the rescaled field chi has no friction term, but it has a time-dependent frequency that has a k-squared term, a term proportional to the mass, as well as this term, a double prime over a, which may become larger than these. Therefore, omega squared goes negative, the harmonic oscillator goes upside down. And the frequency, being the square root of a negative number, then goes imaginary. And at that point, oscillations cease. As you can imagine, a harmonic oscillator with a potential like this doesn't oscillate, it just runs away. So how does that play out for quantum field fluctuations? First, let us establish whether or not the amplitudes of a quantum field have to really fluctuate. And it turns out, in principle, no, but in practice, yes. And here's how that comes about. Consider a real valued function, just a number valued, a real number valued function from R3 into R. And choose a time eta naught. Then let us define the state of the quantum field theory that we call F to be the joint eigenstate of all those field operators phi of x and eta. So the state F, the pure state F, is defined as the joint eigenvector of all the field operators at the time eta naught, with the eigenvalues being the amplitudes of that function F. And there ought to be a vector like this, because the phi's are commuting with each other, so they're simultaneously diagonalizable. So whatever function F we choose, we can find a state in the quantum field theory for which which is eigenstate to all of the phi of x at the time eta naught, with the eigenvalues being f of x. In this case, we know what the measurement of the field amplitude would give. It would give f of x. If we measure the field amplitude everywhere at that point in time, well, the output has to be f of x with certainty, because we have an eigenstate for these eigenvalues. And there would be no fluctuations. Here's how we can see this. Let's first calculate the expectation value. We calculate the expectation value, phi bar, of the amplitude at the position x at the time eta naught, and it's given by this state, left and right, and then the field operator of which we want to calculate the expectation value in the middle. Then the phi hat acting on the f just gives us the eigenvalue. The state f is, of course, assumed to be normalized, and therefore it's just f of x. The expectation values are just as given by f of x. Is there any uncertainty in that measurement? Well, let's calculate it. The uncertainty in an observable, in this case the uncertainty in phi at the position x at time eta naught, and really it's the variance, because it's delta phi squared, is given as usual by the operator minus the expectation value of the operator. So it's the actual minus the mean, and then squared and summed over all possibilities, which is taking the expectation value. In our case, the phi bar is just f of x, as we just calculated. And this phi hat can act to the left or to the right on f and produces just an f of x as well. So it's f of x minus f of x squared, it's all 0. So there are no fluctuations. So it would seem that not having quantum fluctuations in the quantum field is an option. It's like having a position operator and a position eigenvector. If the state is a position eigenvector, there's no fluctuations, you know where the particle sits. But can such states f occur in practice? Not really. They are of interest for theoretical considerations, but in practice, they come with infinite energy. A measurement apparatus would have to have an infinite energy available, because after a measurement of that state, the outcome, if you want to prepare such a state, either by measurement or by other means, you would have to have an infinite amount of energy available. And I leave it to you as an exercise to show that the energy expectation value for any such state is really infinite. So if you calculate the expectation value of h at time eta naught for such a state, it comes out as infinite. I give you a bit of a hint. You see the delta phi is vanishing, but then by the uncertainty principle, the delta pi has to be infinite. But delta pi, the variance of pi, is calculated by calculating the expectation value of pi squared. But pi squared occurs in the Hamiltonian. So the Hamiltonian has pi squared in it, so the expectation value of the Hamiltonian involves calculating the variance of pi, which diverges because this goes to 0. So in principle, we can approach no fluctuation states, but not in practice. And that means in particular that the state f with all eigenvalues equal to 0 also cannot exist, also would have infinite energy. Now that is counterintuitive, because think about it, what is that state? The state f, where the function f is just 0 everywhere, is the eigenstate of the quantum field where we are sure that the amplitude is vanishing everywhere. And what we just calculated is that even that state has infinite energy. So it's not like, yeah, there's a bit of fluctuation and can't be avoided and so on. No, in fact, if you wanted to suppress the fluctuations, it would come at an infinite expense of energy. So that means that all finite energy states do possess quantum fluctuations. No way around it. Now, how shall we calculate the amount of quantum fluctuations? How shall we measure that? by what measure do we have more quantum fluctuations or less quantum fluctuations? And more specifically, we will be interested in answering the question, how many quantum fluctuations are there of a big spatial size, and how many quantum fluctuations are there, or what are the amplitudes of quantum fluctuations at a small size? That, of course, will have to do with Fourier, but it can also be understood very concretely. We'd like to get some good operational handle at what we mean by the scale dependence of the amplitude of quantum fluctuation. And we will do that in two ways. We will give two operational meanings to the fluctuation spectrum of a quantum field. And we start with this idea. The idea is that, as we just saw, it's not realistic to measure the amplitudes of a field at every point individually, because if you could, you'd end up in an eigenstate, which costs infinite energy. And in any case, what kind of instrument would do this? An infinite resolution. So realistically, what we can do is that we can measure the field amplitude by some means smeared over some volume. So instead of trying to measure the field amplitude at every x individually, let's say we measure not phi of x, but we measure phi b, where phi b is the integral over our field over some patch of space. Now here I'm integrating over R3, but don't worry, this is a window function. So this window function is 0 outside a certain region, and therefore this whole expression is just a smeared version of phi of x. Okay? So phi b is just the integral over phi of x over a finite region. That's something that we can realistically hope to measure. And then we can ask, well, what's the expectation value for phi b? What's the expectation value for the average? What's the average amplitude expected in that region? And how much is that average amplitude going to fluctuate? And we'll be interested in the answer to those questions as a function of the size of the region. So if I smear the field over just a tiny region, what's the expectation value? What's the variance? If I smear the field over a large region, what's the expectation value? What's the variance? So we might choose our region, for example, to be a box. At some point later, we will choose it to be a ball, whatever is more convenient mathematically. So for example, we could choose the window function to single out a box of size L cross L cross L, and therefore a particular volume L to the third power. In this case, the window function, W of x, would be approximately 0 or equal to 0. It's not that important that it is sharp. We choose a window function which is approximately 0 for all x that are outside the region. This might be the region that we want to smear over. And the window function might take the amplitude 1 over the volume, 1 over L cubed, for all points inside the region. And we choose the window function to be not 1, but to be 1 over the volume, so that when you integrate over the volume, then you get 1. And later we will also choose this to be not a cube, but a ball of radius L or diameter L. So our plan is to calculate the typical amplitude of the quantum fluctuations as a function of their spatial size. The expectation value will turn out to be 0. The variance is the interesting thing. How much does the mean value fluctuate? As a function of the size of the box. And what we will find is that if we plot here the size of the box over which we smear the field, and here the standard deviation of the measurements of that amplitude in there, then we find that it goes to 0 in this direction. For large boxes, the fluctuations go to 0, which is plausible. We don't see much in the way of fluctuations happening at the large scales that we as humans can perceive. But on the other hand, at small scales, it's actually divergent. Which is why if you go to nanotechnology and then atomic-sized things, quantum fluctuations become very important. And we will also find out that this curve is very much dimension dependent. In 1 + 1 dimensions, it would look very differently. In 26 + 1 dimensions, it would be very differently. In 100 dimensions, it would be very different. The higher the dimensions, the steeper is the divergence, it turns out. And we will find out why that is. And this is still Minkowski space. But then, of course, we will study how the fluctuation spectrum, this is the fluctuation spectrum, how that is affected when space-time is expanding, especially when it's accelerating, which is to say when it has a horizon. And then it turns out that the horizon scale is very special. If this here is the horizon scale, after the horizon scale, it actually doesn't decay anymore. When the universe is expanding in an accelerated fashion, then from the horizon scale onwards, we have that the size of the fluctuations is no longer decaying. And if you compare the two, you see that it's actually an enhancement. For large scales, it's actually an enhancement. And that is ultimately how it was possible that huge inhomogeneities in the universe, much larger than galaxies, that huge fluctuations were still caused, were still triggered in the matter distribution, were triggered by quantum fluctuations of a quantum field. It was that dramatic effect. Yeah?
The Smirnov function seems not to be smooth. Does that cause a problem?
That's why I put here approximately. That gives us the freedom to fudge it a little bit. The thing is, yes, it is not smooth if we make it a strict box. And when you make it a strict box, then its Fourier transform has relatively large frequencies. If we smoothen the edges of the box, then the Fourier transform is better behaved, and we will use all that freedom. In fact, later we will make some approximations for that very reason. Crude approximations, in fact. Isn't that interesting that it struggles here with this flickering? Why would it do that? It doesn't do it on my screen, it's the projector. Okay, so that will be the program. But we will study this fluctuation spectrum not only in terms of averaging over a box, smearing over a box, and then looking at how the mean value changes. We will also study another interpretation of the fluctuation spectrum in terms of correlation functions. Okay, quantum field fluctuations in FRW spacetimes. Let us choose a conformal time eta and co-moving coordinates x, as we've always done recently. Then we choose a region B of size L cross L cross L. And let us keep in mind that this means that we are looking at a box that is growing. If the size of the box is L in co-moving coordinates, well, the co-moving coordinate system is one that's growing along with the expansion. So actually, we are talking about a box of size A of eta times L times A of eta times L, etc. Right? So let's just keep that in mind. Further, let's assume that at the time eta naught, the system state, let's call it omega, is the vacuum state. It's the vacuum state at eta naught. Okay, so at eta naught, we identify which is the vacuum state. And we assume that the system has been prepared in that vacuum state. This could be very early in the universe, for example. Then we choose mode functions. We choose our set of mode functions in such a way that the state that's annihilated by the corresponding A operators happens to be the vacuum state at that point in time. That's a convenient choice.
adiabatic vacuum?
In general, this will be the adiabatic vacuum. So we are assuming here that, for example, early in the universe, we had a phase of adiabaticity, and we identify at that point, at an early point in time when it was evolving adiabatically, we identify which state in the Hilbert space was the adiabatic vacuum. And then we choose our mode functions to be those mode functions whose A operator is annihilating that adiabatic vacuum. So the physics of it is we say, at an early time eta naught, the quantum field was in the vacuum state, as identified via the adiabatic vacuum identification criterion. Okay, so 3 states are the same. The state of the system, the vacuum at time eta naught, and the state annihilated by AK, they're all the same. Okay. So then we can calculate now. You see, this allows us to, what we've done now is we've expressed our field in terms of, we've expanded it in terms of these mode functions and this annihilation operator, right? So we have an expression of the field that's very convenient. And remember that we actually have the field now at all times, right? We have the field at all times, and we know what the state of the field is also at all times. The state of the field is at all times this one. At all times it's this one, the vacuum, whatever state was the vacuum at eta naught. At all times, the state of the system is this vector. Okay, because Heisenberg picture. The state cannot change. So we know what the state of the system is. We know the evolution of the field. Therefore, we can now calculate everything we want later on. Everything. Even if the particle picture breaks down. Even if the evolution is not only non-adiabatic, even if the evolution is such that the harmonic oscillator goes upside down. We have everything. We have the solution of the quantum field theory, and we have the state that the system is in. So let's calculate the expectation value of the region averaged field, so the field in a box near Dover, at some time eta after eta naught. I'm just saying it's eta after eta naught because at eta naught we learned what the state of the system is, the vacuum. Well, let's calculate it. So the expectation value of the smeared field over the region B is given by, well, the expectation value in the state of the field of the operator phi hat B, which you remember is this integral, the 3D integral over the window function at phi. Now the state of the field is the vacuum at eta naught, which is also the vector 0 annihilated by the A operator. So, expressing phi B now in terms of its integral with the window function, and then expressing phi in terms of 1 over A chi. Remember, phi is the physical field that we're interested in. Chi is the field that doesn't have a friction term. We arrived at this expression here. And for chi, we have an expansion in terms of the mode functions and the creation and annihilation operators. So overall, we obtain that this is equal to that. And I forgot the window function. There should be a window function in here. But it doesn't matter because the window function is just a number-valued function. And we can conclude that because the A is annihilating to the right, the A dagger is annihilating to the left, and the A is annihilating to the right, that nothing survives here, and it's just 0. So we conclude that at all times, the expectation value of the field amplitude is going to be 0. So the average amplitude of phi B vanishes in the vacuum state. But what about the fluctuations around the expectation value? Well, it will turn out that we don't always just measure 0 if we measure the average field amplitude in the region. We will find average values, spatially smeared values, that can range very large positive, very large negative. what is the variance? Well, the calculation is very analogous to what we just did. We write down the variance as the expectation value in the state that the system is in, the actual minus the mean value squared, expectation value. The state of the system is really just the vector 0, the vacuum state at the early time. And the expectation value is vanishing, therefore we can just carry forward the phi b squared. The phi b squared is given by 1 over a squared times chi squared. And we can write out what that actually is. It's the chi multiplied with the window function, and then the whole thing squared. So we really have this expression times that expression where we have an integral not over dx, but over dx prime, let's say. This whole expression squared, so we have 2 factors of chi, 2 factors of the window function. And we will need to express this in terms of the creation and annihilation operators. Now, it's a few steps that I leave up to you to fill in. Basically, it's just a Fourier transform that you need to do, but you have to Fourier transform the W, Fourier transform the chi. So you write W as the Fourier transform of its Fourier transform. You write chi as the Fourier transform of its Fourier transform. And then you have integrations over d3x and d3x prime, which give you delta functions and so on. And eventually, you arrive at this conclusion, hopefully, if you do the exercise, namely that the variance of the spatially averaged field phi b is given by 1 over 2a squared. And then this is from the Fourier factors. And then we have that the chi squared gives us a and a dagger operators. And because it's squared, we will have in particular a term of the form ak dagger and ak a dagger. But especially the ak dagger is not annihilating to the right or to the left. It will give us a contribution. And that contribution gives us the mode function squared, modulo squared, and the Fourier transform of the window function, everything integrated over d3k. The d3x integrations can be carried out once you express everything in terms of its Fourier transform. Because then the only x dependence is going to be in the plane waves of the Fourier transform. You can carry that out and get momentum conservation laws, which will simplify, which will reduce the number of k integrations that you have to do. You end up with just 1 k integration. At this point, we notice that it might be useful to choose that window function suitably. For example, such as having a sharp cutoff or a soft cutoff, because that will affect how the Fourier transform of the window function will look like. Okay, so now we have an expression of the variance of the spatially smeared field amplitude. And we can already see that this variance scales, I mean, it depends on the size of the window, depends on the window function. That's what we want to establish. But it also depends on time. It depends on time through the mode function. If the mode function's modulus grows, so does the amplitude. If the mode function's amplitude modulus is shrinking, so does the variance of the field amplitudes. Now, at this point, it becomes simpler if we assume that our region B is spherical rather than a box. Because then we can reduce this three-dimensional integral here to a spherical integral. Namely, if this thing has rotational symmetry, well, that will have. This is just from the quantum field, which has translation and rotation symmetry. So in particular, the VK has the same amplitude even if you rotate the k. Otherwise, the quantum field would be non-isotropic. So that has rotation symmetry. If we give this rotation symmetry too by choosing our window function to be the rotationally symmetric, then we can reduce this three-dimensional integration to a Cartesian integration into an integration in spherical coordinates, where actually the angular integration can be carried out. And you know the surface of a sphere is 4 pi. So what we obtain is an integral over the radius squared, which is k squared, times the carried out integral over all the angles, and it's just the 4 pi. Where this now is just the length of the vector k, and that's the length of the vector k. Now we do an approximation. Let's say that our box or our sphere has radius L. And what that means is that the window function has to decay at about L. And we can assume that the Fourier transform of such a window function will vanish for wavelengths that are larger than 1 over L. The idea is that the Fourier transform being the dual to the window function, the Fourier dual of the window function, reflects the finite support of the window here. You see, this is where the bulk of the Fourier transform is. This length scale is where the bulk of the Fourier transform is. You can think of this as a wave. Right? If you think of the window function as a wave, its wavelength is this. And shorter wavelengths will be suppressed. For example, if the window function was actually sharp, then its Fourier transform is a sinc function. If the window function was a one-dimensional sharp box, then its Fourier transform is a sine x over x or sine kl over kl function. And we will make the approximation here that everything above the length scale 1 over L is vanishing, just to keep our integration doable. So instead of sine x over x, which looks like this, we will basically just truncate everything that's out there. It's a crude thing, but in practice, numerically, you can do better than that. But just to push forward the analytic treatment. What that means is that we will approximate the variance of the field of the smeared field amplitude as being from above this integral here, where we're not integrating all the way to infinity, we are only integrating to 2 pi over L, which corresponds to integrating only in here and saying that the Fourier transform of the window function vanishes further out. Another very crude approximation that, again, numerically, once we are given the VK, we can do better than this. But as long as we don't want to specialize on a particular VK, and we still want to get some nice intuitive formula, let's carry on with the crude approximations. Another crude approximation is to say that in this integral, the main contribution will be from close to the upper limit of the integral. The V may be varying, the VK will take some value close to the upper value of the integral, and it may take other values closer to 0, but those other values won't matter that much because they're suppressed by k squared being small then. So as a very crude approximation, let's just say we use the value that Vk takes up here everywhere over that integral. When we do that, then see if we set this basically a constant, therefore, namely the value that it takes at the upper limit of the integral. If we set this a constant, it has the tremendous advantage that we can integrate that whole integral. And the k squared becomes a 1/3 k to the third power. So that's what we do now. We set the vk, its value at the upper limit of the integral up here. And then we have an integral over k squared, which we can carry out. And we get a 1/3 k to the third power. And we have to plug in this value for k in 1/3 k to the third power. And therefore, we obtain now a closed expression for the variance of the quantum fluctuations. We carry forward this stuff here. And then we have the v squared carried forward like that. The a squared comes here. And then we have 2 pi to the third power over L to the third power from integrating this. And the 1/3 is the 1/3. You get the 1 over L to the third power. And then 2 pi to the third power is over here. So we get some cancellations going. And eventually, we obtain this. So we obtain that the fluctuation spectrum, the size, the variance of the smeared quantum fluctuations as a function of the size of the box is given roughly by this expression, 2 pi over 3 L to the third power, where this is the mode function of the field phi. See, v was the mode function of the field chi. But if we take the mode function of the field chi and divide it by a, we get the mode function of the field phi. Because remember, phi and chi are related just by a scale factor. And the field phi, the quantum field phi, can be expanded in terms of a mode function and creation and annihilation operators, of course, as well. And the mode functions are just related the same way that the fields are related. So omega, or w, I shouldn't say omega, it's w. W is the mode function of phi because chi over a is phi, and therefore the mode function of chi, v over a, is the mode function of phi. So the conclusion is conclusion so far is this. Assume that at the time eta naught, the vacuum state was the state 0 corresponding to mode functions vk. Then the typical amplitude of fluctuations of size L, be they in a box or be they in a sphere, our approximations were so crude we can't really claim that we distinguish the two, at an arbitrary time eta later on is given by this expression, either in terms of the mode function of the chi or in terms of the mode functions of the phi. Now let us look at a special case, just to get an impression here. See, already what we see here going on is, of course, that there's a suppression with 1 over L to the third power, and that the modulus of the mode function is going to be crucial. And also, if you remember how we arrived at this, you can tell right away that this answer is very much dimension dependent. See, this is where it happened. When we went and integrated this k squared, we went to spherical coordinates, right? Initially, that was the integral. See, this was the integral, d3k. And because we went to spherical coordinates, we got a k squared there. And then we integrated that, became a k to the third power, evaluated it at the upper limit of the integral, where it gave us a 1 over L, and that is how we got an L to the third power arriving here. That's how we got an L to the third power. Clearly, the higher the dimension of the space-time is, the higher dimensional the spherical coordinates are going to be, and as we go up with the dimension by 1, this radial factor goes up by 1 power, and therefore this goes up by 1 power. And that's what I anticipated early on, that the higher the dimension of space-time, the worse is the divergence going to be. But of course, we still have a big unknown in this. What are these guys doing? What are the mode functions doing? Because they also depend on L, they depend on eta, and so on. But we get some rough behavior here. We are prejudiced towards expecting huge quantum fluctuations, or at least stronger divergence of quantum fluctuations for small scales, the higher the dimension is. In fact, if you've taken a course, or you may have heard about it, in quantum field theory for particle physics, 3 spatial dimensions seems to be the limit, where we can just about handle the quantum fluctuations through renormalization. If space-time has any higher dimensions than this, any more dimensions than 3, then the quantum fluctuations get out of hand, and there are only very few theories that would still be renormalizable, but our standard model would certainly not be. Standard model of particle physics, that is. Okay, so now let's look at this in a concrete case where we know everything already, Minkowski space. Let's apply the Minkowski space solution to this result. In this case, in Minkowski space, the field chi is the field phi, because the scale factor is just 1 at all time. And the conformal time is the ordinary cosmic time. And we know what the modulus is of the mode function. Because if you remember, the mode function is 1 over square root of omega k. And so if you square it, times a plane wave. Now, if you take the modular square of it, then that plane wave, that exponential e to the I omega t goes away, and we're just left with 1 over omega k. If you don't remember that, please look it up. In Minkowski space, the mode function's modulus goes like 1 over square root of omega, squared is 1 over omega. Now, 1 over omega k, in the case of massless fields, we will discuss the case of massive fields in a moment. In the case of massless fields, omega k is simply the modulus of k. Otherwise, omega k is the square root of k squared plus m squared. Let's, for simplicity, assume the mass to vanish for now. So what we have is that the modulus squared of the mode function is 1 over omega k, which is 1 over the modulus of k, which we can write as L over 2 pi. That's the length scale for the purpose of these formulas here. When we have, instead of plugging in the k, we have to plug in the 2 pi over L. So that means that this expression here, or there, this expression acquires a factor of L over 2 pi. So it's 1 L in the numerator. So this thing provides 1 L in the numerator, which somehow alleviates that concern here with the divergence, but it doesn't get rid of the divergence. It just makes it less bad. Instead of going 1 over L to the 3rd power, it now goes like 1 over L to the 2nd power. Now that was the variance. The variance goes like 1 over 3 L squared. The uncertainty, therefore, goes like the square root of that, which is 1 over square root of 3, 1 over L. And that's the curve that we had earlier. Right? We were predicting that this is going like that. So the uncertainty in the outcome of a spatially averaged measurement of the field goes down for a large spatial area to average over, and goes up for a small spatial area to average over. And it goes like this hyperbola, 1 over L, in the case of a massless field. Okay, any questions so far? No? Okay. Now that was one way of capturing the fluctuation spectrum of a quantum field. We average over a box or a ball, and then we calculate the expected amplitude of the fluctuations as a function of the size of the region that we average over. There is another way of doing it.
If you go to different dimensions, say 1 plus 1 dimension, it seems that curve could be a constant.
Yeah.
And there should be some physical reason to explain it.
Yes. Explain. So let's say we have this here, right? So in 3 dimensions, we have that. In 2 dimensions, we would have L squared here. In 1 dimension, 1 over L. And then we get this 1 over L here, and bang, we have a constant. That's right. Yes. Now, how come? The thing is, basically, you're asking what's the origin of the dimension? The origin of the dimension dependence physically. We saw it mathematically. But what's the physics of it? Now, the physics of it is that in 1 dimension, there are, intuitively speaking, as many modes of small momentum as there are modes of large momentum. You just take the momentum scale, and let's say you put an infrared cutoff, okay? Then you have an infrared cutoff, then you have only discrete momenta available, and the spacing of the momenta is equidistant, so therefore there are as many modes in a certain momentum interval for small momenta as there are for large momenta. It's democratic. However, if you look at, let's say, 3-dimensional space, 3-dimensional momentum space, again, infrared cutoff, again, the momentum becomes discretized, again, the allowed momentum vectors are equidistantly spaced as a rectangular grid. But if you now ask, how many momentum modes, how many momenta are allowed in a certain momentum interval, modulus interval, in 3D, well, you find that there are much fewer for the small momenta than there are for the large momenta. So, any shell of a certain delta momentum will contain more and more momenta the further out you go. And that's why you get this extra measure factor of k squared, k to the third, k to the fourth in the Fourier integral, which makes things worse. And so the real reason why quantum fluctuations become worse in higher dimensions is not that by nature they are more aggressive or anything like that. No, there are just more of them. Just way more of them at the large momenta and therefore at the short distances. Just because momentum space has way more dots, discretized momentum space has way more dots in a certain shell of a finite momentum range than if the shell is large radius than if it is small radius. Right. So in fact, most theories are very nicely renormalizable in smaller than 3 dimensions. Which is also why it has been speculated that maybe the ultraviolet divergences of quantum field theory can be regulated by assuming that space-time really has a lower dimension when you look at the ultraviolet, when you look at very small distances. But it hasn't turned out to be the solution either. So let's look at another way of studying the fluctuation spectrum of a quantum field. And here the idea is, as a function of the size, here the idea is not to smear over field amplitudes, but instead it's a different approach. It's an approach that's basically inspired by electrical engineering. So we'll do 5 minutes of electrical engineering now. And the idea is basically this. Imagine you have some sort of signal on your wire or coming through your communication channel. And for the moment, let's just think of noise. After all, quantum fluctuations are some kind of noise. Then it could be an image, so it could be in space, or it could be noise in time. Noise in space, noise in time, doesn't matter. Now, imagine you measure the noise here, and you measure the noise there. Separated in space or separated in time, doesn't matter. Then you can ask, if you keep repeating those 2 measurements, and the noise keeps changing, And then you can ask, how correlated are they? How correlated is my noise here with my noise over there? If I find a positive number there, how likely am I to find a positive number there or a negative number there? And the correlation function is, of course, the average of the product. Right? If you take two random variables, take their product and calculate the average of that, that gives you the correlator. If they're uncorrelated, the average product is 0. Because if one is positive, the other one is equally likely to be positive or negative. So you either get a positive or negative contribution, but with equal probabilities, so the correlator would be 0. And we can do that in quantum theory too. But let's first do it for electrical engineering, basically, or I mean, it's just an engineering concept. But we'll apply it nevertheless here. So let's assume that n of t, a noise function, is omega band limited. So let's say n of t is a noise function in your electrical cable, let's say, if coming from the microphone or whatever, and it's band limited. So it has no frequencies above capital omega. And let's assume that it is Gaussian white noise. Gaussian means that the amplitudes are Gaussian distributed, and white noise means that all frequencies occur with the same power, up until the cutoff given by the band limitation. So this would be a random signal with Gaussian distributed amplitudes filtered to only frequencies in the interval from minus omega to omega. Then for an ensemble of such noise signals, one can show that the average value is 0. Well, obviously, because the Gaussian is just as much positive as it is negative. Yep.
So how are we redistributing the weighting for throwing out the bandwidth, or like the band limited part?
Well, you just filter it. You create that signal and then you pass it through a filter so that you could basically take the Fourier transform of it, setting all the frequencies higher than, and then Fourier transform back. A lot of noise is of this form. Not all of this noise is of this form, but a lot of noise is of this form. Okay, so then, as I said, the expectation value is 0, but the crucial correlator is what? The correlator is this. It's the expectation value, that's why I put a bar over it. It's the average value, or the expectation value, of what the amplitude of the signal is at time t, and what the amplitude of the signal is at time t plus L, a little later. And it turns out that for such a Gaussian white noise signal, the correlation function is up to a constant sine of omega L over omega L. The constant depends, of course, on how loud you make your signal. Right? So that's nothing particular. You can choose it whatever you want. You just change the loudness of your signal. So the correlation function is this, which means that the correlation is perfect with itself. If L is equal to 0, then this is just sine of omega L over omega L, which is 1. And then if L grows larger, then you find that the correlation goes down, and it goes down like a sinc function, like a sine x over x function. The further away the 2 points are in time, the less correlated they are. And you can also see that there's an alternation between positive correlation, negative correlation, positive correlation, negative correlation, and so on. But it pretty quickly decays. But how does one calculate such a thing? Now, here's how we calculate that. This noise, Gaussian white noise, is ergodic. And what that means is we could, instead of repeating that measurement, repeating that setup, and whenever we repeat that setup, we measure at time t and at time t plus L. Instead of doing that, we can also simply integrate that over time. Basically, instead of having one Gaussian white noise, and then another Gaussian white noise, and then another Gaussian white noise, and each time we measure, for each of them, we measure at time t and at time t plus L. No, that noise is translation invariant. We might as well, instead of throwing away the noise and taking another one, we might as well just integrate along the noise. Okay, so what we do is, in order to calculate that average, we calculate the product of the noise signal and the noise signal a little later, and we integrate over all time. Now, obviously, we may have to regulate this, because if the signal is just keeping its amplitude forever, then this might come out infinite. So in that case, we would integrate not over the entire time axis, but we would integrate from minus capital T to plus capital T, and then divide by the length of the interval, so we get the average value. So that comes out finite then. And now comes a crucial calculation that is useful for a lot of understanding of what correlation functions are. So we are calculating this average by integrating over all time. For that purpose, we write f of t as the Fourier transform of its Fourier transform. So we write f of t as f tilde of omega Fourier transformed to the time variable. We also express f of t plus L as the Fourier transform of f tilde of omega prime Fourier transform to the variable t plus L. And then we have three integrations, right? We have the omega integration, the omega prime integration, and the t integration carried forward. Now the only t dependence, after we've done that Fourier transform, the only t dependence is in those plane waves. So we can integrate out that t integration, because we can simply collect this t dependence and that t dependence, and that gives us this plane wave factor here. Everything else is as before. We just collected these things, and now we integrate over t. And when we integrate over t, actually there should still be dt here, then this just becomes a 2 pi delta function, 1 over 2 pi delta function, right? Because if you integrate a plane wave, it gives you a delta function. And that in turn means, because now we have a delta function in omega plus omega prime, it means that we can integrate out the omega prime integration. And we're just left with one integral over omega. And this is what we get. Very important result. We obtain that, just go back, okay. We obtain that the correlation function, so the correlator, as a function of the distance between the 2 points in question, is given by this integral here. What is this? We have here the modulus squared of the Fourier transform of the noise. Okay, so f was the noise, f tilde is its Fourier transform, and we take the modulus squared. And then that modulus squared is Fourier transform. The modulus squared of the Fourier transform is called the power. It's called the power of the, in engineering literature, of the signal, of the noise signal. And so what we see here is that the 2-point correlator, or also autocorrelator, because the noise is correlated with itself, autocorrelator, the 2-point correlator is the Fourier transform of the spectral power function. Okay, because we take the spectral power, it's the power in the spectrum, it's the modulus squared of the spectrum, and we Fourier transform that. That's an important relationship in electrical engineering. So for example, for white band-limited noise, remember the definition of white band-limited noise. It is noise whose spectrum is simply a box from minus omega to omega, with all frequencies contributing equally. And if we Fourier transform that, we obtain the 2-point correlation function, which is a sinc function, sine of omega L over omega L, as we had claimed earlier. Now, quantum field theory. Oh, maybe let me show you something. As a little experiment and an open question too. I have an app here which is calculating the Fourier transform. It's calculating the Fourier transform on the fly. So if you speak, it will give you the Fourier transform. Okay? Now have a look, when we are very quiet, have a look at the curve. See, it reacts to the voice, right? But look at the left end of it. It hyperboles upwards. Right, you see that? This is the above curve is just the peak. And it turns out that this is a very general phenomenon. Noise typically has 1 over f. It has 1 over omega behavior at the low frequencies. Not every noise, but for example, electronic noise like this typically has that. And it's not clear why that would be so. See, the observation is that this thing, it goes like 1 over omega. Or 1 over omega. But that is weird because that doesn't have a Fourier transform. That's weird. It's not clear why that would be. The physical origins of 1 over f noise are not fully understood. There are theories for various circumstances, but it's a very simple thing. And yet there's still some mystery about this, even though it's all classical. Probably no quantum in this. It's probably all somehow thermal noise, but why it conspires to be 1 over f that's the mystery. Anyway, so we're looking here at the case of quantum theory now. Oh, and by the way, if you want, play around with it a little bit with this result that the Fourier transform of the power spectrum gives you the autocorrelator. For example, when you listen to a waterfall, typically the noise will be what is called pink noise. And that has a particular shape here, and then you can Fourier transform that. And you see, it has more, pink means it's not white, so it's missing, so to speak, blue frequencies. So it's decaying this, towards the larger frequencies. And you can now just Fourier transform that and then get the two-point correlator. And that tells you how the splashes of Niagara Falls are correlated to each other over time scales, right? Anyway, so that's the relationship between the power spectrum and the correlator. So now let's look at correlators in quantum field theory. I should really put a picture of Niagara Falls in there. Anyway, two-point correlator in quantum field theory. We take, for that purpose, we take the expectation value, but now the quantum expectation value of the field at one point and the field at one point at the same point plus a shift by a vector L. Okay. Plus, okay, so the field at two different positions, but at the same time. Then we express the field phi in terms of the field chi. And we can use then the mode expansion of the field chi and spherical coordinates, because the whole thing is, of course, rotationally symmetric. And then you can derive, just by plugging in the mode expansion of chi and the fact that the A operators annihilate, the A dagger operators annihilate to the left, and there will be products of A and A daggers, and in particular there's one product which is A times A dagger, and that will contribute here, and that will give us that expression here. No approximations at this point. And again, we have a dimension dependence here. The k-squared factor has a 2 appeared because we have 3 spatial dimensions and we went to spherical coordinates. And the mode function comes up here. And the sign of KL over KL just comes about from the plane waves that arise with the mode functions in here from the, as you go from the spatial dependence to the momentum dependence. There's a Fourier transform, and that will give you this expression here. So now we do some crude approximations again. Namely, we will approximate the sinc function as being 1 up to the scale k equal 1 over L, and being 0 outside of that. That's very similar to the approximation that we did for the smearing over a box integral. And also, we will make use of the fact that this factor here has its main contribution around k equal to 2 pi over L, as you can just check easily. And so we arrive at a crude estimate, and you can see how this is a parallel crude approximation to what we did with the smearing over a box. Namely that the 2-point correlator for a quantum field is given by 1 over a squared from the change from phi to chi. Then that integral, where we integrate up to 2 pi over L, we make the approximations that we did earlier as well. And we arrive at k to the 3rd power, some denominator, and the mode function squared, where again we're evaluating the mode function where it contributes most, which is at k equal 2 pi over L. Let's look at Minkowski space. In Minkowski space, in a massless case, the mode function is given by 1 over omega k, which is to say by 1 over the modulus of k, if there's no mass. And therefore, if we plug it into the formula above, then we obtain that, again, the correlator is just 1 over 3, 1 over L squared. Which happens to be the same result that we had earlier for smearing over a box. The predictions just happen to be the same. The prefactors, never mind, we did crude approximations for them anyway. But the overall scaling behavior is curiously just the same. So we can now plot a curve like this, where we have the size, not of a box. No, now it's the distance between 2 points where we calculate the correlator. And here's the correlator upwards, the square root of the correlator. And then we get, again, a behavior of 1 over L. So we notice that the variance in a box, or actually the standard deviation in a box, scales like the correlator. And both are good measures of the fluctuations. So we define simply then, we define the so-called fluctuation spectrum at time eta as a function of k to be, by definition, whatever we calculated for those two. Namely, 1 over a, k to the power 3/2 mode function. Modulus of the mode function. It's just the square root of what we just calculated. For the correlator, it's the square. For the variance, it's the square of it. We take the square root of it, then it's that. So that is the power spectrum for quantum fields, and you can interpret that as the square root of the correlator, or you can interpret that as the variance, not the variance, the standard deviation of measuring fluctuations in a box of size 1 over k, or 2 pi over k. Now let's look at the special case of Minkowski space with massive fields. The scale factor is, of course, 1 for all times. The mode function is given by this. And omega k is now square root of k squared plus m squared. So the fluctuation spectrum is then by definition, remember, here's the definition of it, So the fluctuation spectrum is given by 1 over a, k to the 3/2. So, and the mode function, the modulus of the mode function. So we get k to the 3/2, and then we get 1 over the square root of this. And right, I was just checking where the a went, but it's Minkowski space, and a is 1. Okay, so the fluctuation spectrum for Minkowski space for a quantum field with a mass is therefore given by this expression here in terms of momentum, where notice that if the mass was vanishing, then we would have here k to the power of 1/2, which cancels a half from the k to the power 3/2. So it would be k, which is 1 over L, right? It's the 1 over L that we talked about earlier. But now it's a bit more complicated. There's this extra mass term, so this cancellation is not as simple. Now, of course, if k is very large, if we're looking at very small wavelengths or small correlation lengths or small boxes to average over, then when k is very large, so it's very small scales, this term dominates over that, and we can still cancel things easily, and so we just get a k here, which gives us the 1 over L behavior. So that is for k going to infinity, that's in the ultraviolet. That's why we say that in the ultraviolet, masses don't matter for the purpose of quantum fluctuations anyway. However, for small k values, it's this value that dominates. So instead of having the k squared being dominant, now it's the m. And the k squared is small. So in this case, we have a behavior like k to the power 3/2. So what this is saying is that for small k, the behavior is k to the power 3/2 or L to the power of minus 3/2. L to the power is minus 3/2. And that is a faster decay than L to the power minus 1. So if we express that now in terms of, it's better to show it all like this. Okay, so large k means small l. For small l, we still have the k behavior, which is the 1 over L behavior. So at short distances, it's 1 over L with or without mass. But then for large distances, we have a behavior like k to the power 3/2, which is the power of L to the power minus 3/2. So at large distances, the decay is actually faster than it was before. In other words, in the ultraviolet, masses don't matter, but in the infrared, at large distances, masses suppress the quantum fluctuations. It makes them go down faster. Now, in this picture here, it's very difficult to draw, and just as difficult to see that this goes here like 1 over L, and then here it goes like 1 over L to the power 3/2. I mean, can you tell the difference? I cannot. So we need to plot these things a little bit nicer so that that behavior becomes clear. And for that purpose, we can use log-log plots, which take a little getting used to, but I suppose you've seen those before. So let's say we choose as our x and y coordinates on our plot now, the x coordinate to be the log of k, and the y coordinate to be the log of the delta phi k. So we take the logarithm of both, the x and the y axis. Or the x and the y axis are the logarithms of what used to be the x and the y axis. So we have that the logarithm of delta phi k, so on the y side, we have the logarithm of k in the one case, and we have the logarithm of k to the power 3/2, which is really 3/2 the logarithm of k in the case of small k's, which is large L values. And So what we have is that y goes like x, namely like the logarithm of k. Remember, the x variable is the logarithm of k, and our y variable goes like the logarithm of k. So we have that y goes like x for for x going to infinity, but x is the logarithm of k, so for k going to infinity. But we have that y goes like minus 1/2 ln m plus 3/2 x, from comparing with this, for x going to minus infinity. The main thing is that we have that as long as we have a power law, it's going to be a straight line. It's going to be y proportional to x or y proportional to 3/2 x. Here it's capturing the slope of the curve is 3/2. Here the slope of the curve is just 1. And so what we obtain is a plot, a log-log plot, where we have that for large k, for small distances, therefore, we have the 1/L behavior, which is a straight line where the slope is 1, and that indicates the power of k to the power 1. And that gives us the slope 1. And here we have k to the power 3/2 as the scaling behavior, and that translates into a straight line with slope 3/2 in a log-log plot. And so we see the transition here happening, and the transition happens where the mass kicks in, where the mass becomes comparable with the k value, and on a log scale, this is where the log of the mass is sitting. So usually, such transitional behavior is plotted in a log-log plot. Now for cosmology, the mass is actually not going to be very important, but for completeness. Okay, so we notice that in Minkowski space in particular, large-scale fluctuations are strongly suppressed because they go down like 1/L. And if there's a mass, then they're even stronger suppressed because they go down like 1/L to the power 3/2. The mass, now some comments about the infrared. So we saw that the mass does not matter very much at short distances in the ultraviolet. In the ultraviolet, with mass or without mass doesn't matter. But for large L, the mass term helps to suppress the quantum fluctuations. This is, what I wanted to say here is that the phenomenon that we just found, namely that in the ultraviolet, for large K, masses don't matter for an estimate of the amount of quantum fluctuations, was used by Weinberg to introduce a method to quickly check whether or not a candidate quantum field theory is renormalizable. In other words, whether the quantum fluctuations can be handled or not. And it's called the method of perturbative power counting. And it's a crucial part in it is forget about the masses, just count the number of powers that you have in momentum integrals in the denominator, and from that you can estimate whether or not you can handle the divergences that arise. That's what it's based on, even though in particle physics courses you usually don't calculate the quantum fluctuations like that. But here we see ultimately what the reason is why power counting works. Regarding the ultraviolet, we see that quantum field theory predicts divergingly large quantum fluctuations in measurements that resolve smaller and smaller regions. Which is why we expect that something happens that our theories do not describe yet at very, very small regions. So for small enough regions B, the fluctuations in the amplitude of a field would eventually lead to fluctuations in the Klein-Gordon field's energy momentum tensor that are large enough, in principle, to do any kind of damage to the space-time, could even create black holes. And therefore, at this scale, And back of the envelope estimate shows that the scale is 10 to the minus 35 meters. The Planck scale, we expect that the notion of distance is breaking down. We expect that all these calculations are no longer right. Basically, as soon as we are in this plot here, take this one, we don't really trust that plot when the length scale becomes as small as 10 to the minus 35 meters, because then the quantum fluctuations of the field, and especially of the energy momentum tensor of it, do not allow us to still claim that all of this quantum field theory business happens on a background space-time that doesn't care. When the fluctuations become large enough, they will translate into fluctuations of curvature because of the Einstein equation. And then when the curvature and the metric are fluctuating very wildly, then we don't even know what it means to speak of a short distance. If you have 2 points, and in between the 2 points, you don't know what the curvature is, then you cannot know what their distance is either. So things break down somewhere over here, and we don't quite know what the proper theory is of what happens then. But unfortunately, we cannot measure these quantum fluctuations all the way down. With particle accelerators, we can measure length scales down to about, 10 to the minus 19, 10 to the minus 20 meters now. Cosmic rays come with even more energy, but it's more difficult to measure what they do. But they come with like 4 or 5 orders of magnitude more energy. That gets us a little bit further down there, but it's still like a dozen of orders of magnitude to the Planck length. More than a dozen. But in cosmology, we will actually get very close there. We will get close to about 4 or 5 orders of magnitude to the Planck scale. Because the horizon, the size of the horizon during inflation, should be only about 4 or 5 orders of magnitude larger than the Planck length during inflation. Which is also why there is a chance that inflation might have picked up some signature of Planck scale physics. And a lot of people, including myself, are pushing the idea that this is our best hope for experimental access to the Planck scale. Namely that whatever the quantum fluctuations are doing here at the Planck scale, involving space-time and fields and so on, it could have left an imprint on the cosmic microwave background that was generated when the horizon was only 4 or 5 orders of magnitude away from the Planck length. And so it may be our best shot at Planck scale physics. But exactly how to do that, well, we'll see later in the course how we calculate the quantum fluctuations for the CMB and where there's an entrance for possibly checking Planck scale physics. So if one day when you work on a quantum theory of gravity, and you can use what we do in this course to check what it would imply for predictions of the CMB. Okay, so that's it for today.